we will discuss the basic things about functions, because in the next unit, in the 5th unit, we will do the differential calculus introduction. So using calculus to understand functions cannot happen if we are not familiar with the general ideas about functions altogether in general, in principle. So this is what we are going to do this week. Maybe some of this will be postponed for Monday if we cannot manage absolutely everything. But in principle, this week we are dealing with functions today and Friday, and then next week we will start considering limits. There are other administrative issues, but I see that at the moment there's not enough people. As always, some people are running very late, and then I see there's some people who are not signing in yet. So if we have 33 students online and only 26 have written their names, so I will assume that those who switch on their computers and are not present, evidently. All right. So now, regarding functions, just a moment. I need to see what's happening with my tablet. We might have a slight problem. Let's see. Better now. All right, there we go. So let me just have a look at the color. I need my white chalky color. And so there we go. So today we will discuss the main properties of functions mostly, hopefully also composite and inverse functions, and then the very specific functions and the very specific things that we are doing with functions will be left for the next time. So what is a function altogether? When we think about what is a function, the general thought of what it actually is usually people say, oh, function is y equals x squared or something, a formula. The function is not exactly a formula. A formula is a representation, perhaps, of a function, but a function is a relation between x and y, between two variables at least. We might call them x and y. That's what we usually do. Sometimes we use different names for these variables, but not always. So usually we say x and y, so a relation between x and y, which means they are connected. And also y depends on x. So these two variables are connected and y is dependent on x. So for each x, there's a unique y value. For every value of x, we can find one and only one y value. Of course, for some x values, the y values don't exist. That's something that we will discuss in a few minutes, in a few moments. But a function is, first of all, a relation, not the formula, not the equation, not something else, but exactly this relation, the idea that y depends on x, and the idea that for every x value, there's only one y value possible. We cannot say that for x is 3, y could be 5, y could be minus 5 or 4. That's not a function then. For every x value, just one possible y value. Only then we call it a function. There are other relations possible that are not functions, and perhaps later we will have a look at those as well. But at the moment, y depends on x, which means the x is called the independent variable, or sometimes it's also called the argument. The argument, I have already written it there, I didn't notice, sorry. And y is called the dependent variable or the function value. So the independent variable, the argument, and the dependent value, or what we say the function value. X is the independent value, y is the dependent value. And the set of all x values is called the domain of the function, the domain of the function, and it is denoted by d of f. That's just as I said in a minute or 2 minutes ago. Not all x values have the function value defined or possible even. For some x values, the function cannot be found at all for different reasons. It's also possible that for practical purposes, being engineers, being scientists, we need to somehow limit the domain. We don't need all the possible x values. We only need a certain range of x values. We call this range the domain. So the domain could be natural, that is, anything that the equation or the definition of the function allows, or it could be somewhat artificial when we set the domain of this function will be from x equal to 0 to x equal to 10 and nothing outside. That's also possible. And sometimes we will actually need to do this. The purposes might be different. Some of them practical, engineering, science. In science, perhaps a certain process can only start above certain temperatures, like boiling, for instance. Or we are only interested in a certain segment of time from the 0 moment till 20 seconds, for instance, when x is time. So we need to somehow limit the domain of the function. For practical purposes, it is of course possible. Sometimes it's for mathematical purposes. In order to be able to do something, and we will see later, to find, for example, the inverse function, we will need to consider the domain because it's not always, otherwise it's not always possible. The set of all y values is called the range. So the domain is, let's say, indeed the domain, the interval where the function is defined, the x interval or the x set. And then we have the set of all y values called the range. So how far can this function reach? The range of the function. And also going back a little bit to the previous slide, this notation, f of x, it actually signifies that y is a function of x. And sometimes we actually write that f is a function that to every value of x assigns a specific value of y or maps x onto y. Mapping, function as a mapping. For each x value, we get a corresponding y value. That's what we call a mapping. The relation between x and y, the dependence on y on x, or we could also say mapping. We could also say mapping of a function. So to use this f of x, it means that the function of the independent variable x. And that means that for every x specific value, we can apply the rule as it is stated by substituting that x value into the, sometimes as we say, equation. So I need to remind you that a function is not always defined an equation. Sometimes you could define a function by just graphing, by registering the specific values. For instance, as you register the temperatures, if you have an automatic registration of temperatures, the automatic registration of the whatever the thermometer shows, for example, in weather stations, basically it is registered automatically what happens, what the temperature at this point is at any given moment. And that's not a formula. You don't find the formula. In economics, the economical functions of, for example, demand and supply, they are practical functions. They happen as they happen, depending on the price. So when you want to when you want to sell some product at a certain price, the demand will depend on the price. The more expensive this object, this product is, the less people will be willing to buy it. There are exceptions, but in general, the law of economics is that. And of course, the more expensively you sell it, the higher the price, the more suppliers will be willing to sell this, of course. if you can earn some money. So the supply function actually increases with price, the demand function decreases with price. However, there is no formula because it depends on the people, on the ability of people to buy, for example, on the financial resources of the people in the location where we are doing this. So it's not something you can describe with an equation. So that would be function determined experimentally by simply registering the data, by, for example, making the value table for that function. That's also a possibility. It's not recording. Okay. Let me check. All right. Yes, now it should be recording. It should be recording now. All right. So let's go on. The graph of the function. Evidently, the graph of the function is very similar to the curve in, let's say, Cartesian equation, in Cartesian coordinates. Remember that we also had a curve was actually described as a locus of all points having a certain property. Here again, it's the locus of all those points whose coordinates satisfy the equation, which is basically the same as with the analytical geometry where we had curves, points that whose coordinates satisfy the equation. Only the main difference here for this, the difference for this is that it has to be a function. That is, every x value must have one and only one y value. If you remember, then, for example, the second order curves that we discussed last unit are generally not functions. They are not graphs of a function. The only difference could be please switch off your microphone. Please switch off. Now, please switch off your microphone. So, the graph. Kunal, please switch off your microphone. Are you there? People, please switch off your microphones. I will not continue with this background noise. I'm assuming, Kunal, you are not there. Okay. So now, I was talking about the second order curves, that are, as you know, an ellipse. So for an ellipse, an x value actually possesses two y values. It's possible to have this problem. The hyperbola with the hyperbola, remember the hyperbola, is the same thing. An x value can have two y values with a circle the same. The only exception is the parabola, where we had, if the parabola opens vertically, then of course the equation does describe a function and the parabola could be considered the graph of a function. So the idea of a function as a graph, the graph as a representation of a function, actually also shows this idea. The vertical line test, the so-called vertical line test. You can draw a vertical line through the graph. If this vertical line intersects the graph at one and only one point, then this graph represents a function. However, if any vertical line intersects the curve at more than one point, then we see, oh no, that's not a function because that particular x value has two corresponding y values or even more, so that would not be a function. However, if we deal with polar coordinates, we could also say that, yes, but perhaps we could view the ellipse as the graph of a function, because if we look at an ellipse in polar coordinates, then for each angle of rotation, we have only one polar distance. We have only one polar radius. So the polar radius depends on the angle of revolution in a functional way. So in Cartesian coordinates, the vertical line test works. In polar coordinates, you can imagine if we have a polar function, then we have to think about a different kind of rule. It's not exactly the same. So how we define this function, in which coordinates, what rule we use, also determines the idea of a function. So generally, the ellipse would not be a graph of a function. However, in polar coordinates, we can write a function which does not work in Cartesian coordinates as a function. Now, increasing and decreasing functions. So what can the function do? What can we do about a function? In this graph, we see an increasing function. So what does that mean? How would we describe an increasing function in words? At least, how do we understand a function that is increasing? The graph goes up. Could be, we could say it like this, the graph is going up. What does it mean mathematically? More mathematically, the graph going up. As x goes in the positive direction, as x moves on, or we could think as time goes on, the value of the function increases. Which means if x increases, that is, the second x value is greater than the first x value, it means the function value also increases. That is, okay, sorry, that was x1, this last thing. Need to improve the situation. Okay. Then the function value at the second point will be greater than the function value at the first point. This is a mathematical description of increase of a function, of an increasing function. In other words, the function is called or said to be increasing on some segment of the domain, because it doesn't happen all through the domain, perhaps. If for any two x values from this part, from this segment, for example, we could consider the segment from 0 to, let's say, this point, whatever that is, C, from 0 to C, segment from 0 to C, the function is increasing on this segment, because no matter which two x values we take from this segment, if the greater x value has the greater function value. And at the same time, the function could be decreasing, which means as x moves on in the positive direction, the function value, however, we see goes down. That means, in this case, x2 is greater than x1, we choose any two x values, and if the x value increases, the function value, however, decreases. The function value at the greater x value is less than the function value at the smaller x value. So the definition for decreasing on some segment of the function would be, of the domain of the function, would be if for any two values from this segment, no matter which values you pick, the greater x value has the smaller function value. In other words, this first part, as you see, is exactly the same for both definitions. So we assume that x1 is less than x2, or that x2 is greater than x1. Putting simply, as x increases from x1 to x2, the function value does this or that, either increases as well, which means the function is increasing, or does the opposite, decreases. When increasing the x, what happens to the function value? And this is how we can write this very, very mathematically. Or we could say the positive increase of x, if we denote x2 minus x1, this difference between the two x values, by delta x, and that's something that we will see a lot in the next unit. These deltas will be present a lot. So if delta x is positive, if delta x is positive, then what happens to the function, the corresponding delta f? And I can write that delta f could be defined as function value at the second point minus function value at the first point. So in this case, we would see in the first case, we would see that delta f is, as we see, the difference between these two values of the function. So what is the total increase of the function? And it's positive because the function increases. In the second case, we see that the delta x will be negative because we subtract smaller minus greater value of the function. So in the second case, the delta of function, the difference, the increase, or we call it the increment of the function, is negative. So this means that for increasing functions, the positive increment of x implies a positive increment of y. And in the decreasing function, a positive increment of x implies a negative increment of y. As the x values increase, the x increment, the delta x, the value of this difference, this is delta x, the value of this difference is positive, that is, x increases, the function value, the increment of the function is positive if the function goes up, if it actually increases, second value greater than the first value, and down if it decreases. We will discuss more about the increments in the next unit. However, now this is why we are discussing it. Increasing, decreasing functions, so that we can deal with the next unit with dealing with differentiation, with the behavior of the function depending on its derivative. And let's so to say that an umbrella term, one word for increasing or decreasing functions is monotonous or monotonic. A monotonic function on a segment means it does not change the direction. It's all increasing or all decreasing on that segment. So we will also talk about intervals or segments of monotonicity that will be for functions that increase and decrease. So that would be that for some segments of x, the function increases. For some other segments of x, the function decreases, then increases again, decreases again, and so on. So we call these intervals of monotonicity, interval of increase, interval of decrease, but they refer to the x intervals. So you might think of x as time, even when we are not talking about time, we are talking about normal, regular mathematical functions. But we could say at which time did the temperature rise? At which time did the temperature fall? If we are talking, for example, for measurement of temperature outside the window. So those would be the intervals of monotonicity, monotonic functions, that is, just increasing or just decreasing, but of course not forever and not always. Next, properties of functions. Some functions could be odd or they could be even. So what does that mean? An even function, you are probably used to dealing with odd and even numbers. Odd numbers like 1, 3, 7, 11, and even numbers like 0, 2, minus 8, 100, and so on. So what about the functions? How can functions be even or odd? The name even and odd is it seems slightly perhaps strange, but it has a very good reason, and you will see why we call them odd or even. And that would be if we have opposite values of x, then for an even function, for all opposite values, the function values are identical, they are equal. So you see what happens here in the graph, for example. We say that, okay, two opposite x values, x and minus x, and for each such pair of exactly opposite x values, let's say this is x and this is the corresponding minus x, we see that the function value is exactly the same for all such pairs. You also see that the graph is symmetrical against the y-axis. So that's an even function. The most common example for even functions is, let's say, a function, the power function with an even power. For example, y equals x squared, y equals x to the fourth. So even powers. This is where the name even comes from. But of course, there are other functions as well. For example, the trigonometric function, the cosine function, is even. It's not a power function, but it's still even. The function absolute value, the function y equals modulus of x, it's an even function because all opposite values of x have the same value of y. So in this case, the name even comes from the even powered functions, but in actuality, it might be more than a power function. It doesn't have to be a power function. It could be actually something else. Cosine, some other functions that we will deal with will be even. And odd function. So now probably you have an idea what's going on here. If even function, the name even function comes from the even powered functions, then what happens with the odd powered functions? Then when we change the value of the independent variable of the argument x, the function value itself switches to the opposite, changes its value to the exact opposite. The graph would be, for example, like this. That means, so C, we have, for example, two opposite values of x. Let's say this is x and this is minus x, because x could be negative, then minus x is positive. And you see how the corresponding function values are exactly opposite. This means the graph is symmetrical with respect to the origin of coordinates. So we have two types of symmetry. We have the symmetry in a line with respect to a line, and we have the symmetry with respect to a point, or axial symmetry, line symmetry, and point symmetry or central symmetry, this kind of thing. And of course, the typical examples are y equals x cubed, y equals even just x, y equals x to the fifth. So those graphs. By the way, talking about the graphs, I will upload after this lecture, I will upload the whole fourth unit. In the first lecture file, you will have, let's say, an appendix or a third page, if you like, or third and fourth page. You will have 2 pages of with a table, the table of basic elementary functions. That is, all these functions will have examples of graphs, the description of domain and range, and the general behavior. Those are the functions that are familiar to you from high school. Keep that printed out, keep it handy, because that is like a manual, like a reference material for all the functions that we will be dealing with. The shape of the graph of each function is extremely important. In the future, we will be discussing functions, their behavior, and much more, even for the limits. So you need to remember the graphs of these functions, the basic graphs, the basic properties, what they generally look like, the shapes, and so on and so on. So that will be uploaded. I will probably upload it as a separate file, this table, so that you can download and print that out without having to print out everything else. But that's something that is very, very handy including tests, exams, and all that. This sheet of functions and their graphs and their properties. And you will see the basic graphs of even functions, even powers generally look not exactly, they are not parabolas. Only the quadratic function gives you a parabola, but they have this U shape, and the function with odd powers have this shape similar to the cubic function. And then, of course, we have several root functions, other kinds. Those will be discussed somewhat later. They can be even, they can be odd, they can be just a general function that is neither even nor odd. Because this has to be true for all x values from the domain. For all x values from the domain, but there will be functions which simply are neither even, this doesn't work. Opposite x values do not have equal y values, and opposite x values do not have even opposite y values. They have completely different y values, or maybe they have one of those x values no y value, they don't both belong to the domain. Those are simply general functions, neither odd nor even. We can say general function, not odd, not even, it's general. Now, another matter, composite functions. If we generally can consider a function something like a black box, something like a black box, for instance, that would mean that we put in a coin, or a number x, and the function simply spits out a token or an object. Or if you can think about these vending machines where you buy soft drinks or where you buy snacks, for instance. So basically, whichever number you enter or a coin you put in, depending on that number, it spits out the value. In other words, the thing you are buying, whether it's a bottle or a can of soft drink or a bag of chips or a chocolate bar or something. And composite functions simply act somewhat differently. For example, you have two machines, and into one machine, you could. I am sorry. I think I have. Okay, just a moment. I need to go out. Of this because I think I have hidden some of the slides. Sorry. One moment, pause share. Then I go out of this. Oh, I see. Okay. I see. I have slightly confused order. That's all right. Okay. I can resume the share. There we go. From current slide. All right. I thought I had confused my slide order, but it's okay. So we will start with an example. That's all. So we see a function f of u, but to get that u, first of all, we have to perform another operation. In order to get that u value depending on x. It's like take a coin, put it into one machine, it gives you some kind of token. And then you take that token and put it into the next machine, and depending on the value of that token, on the type of the token, it gives you whatever good you want, whatever product you want. So it's like a double box. In this case, for example, if we look at this, we can think in terms of, all right, g of x as a function must go into f. In other words, I take the function g of x found from x and put it into the y function instead of u, which means what we have to do with the g function is squaring. Okay, I will write it in general later, but in this case, it will be y equals f function, means we square the u value, but the u value is this. So we write 1 over x plus 1 squared. So now this is my y function totally dependent on x. This is a composite function. So in general, we could say that we, first of all, we take x, we map it onto u, that is, we use the g function, the interior function, we call it the interior or the inner function. We use this, apply the function g to find the u value as the value of function g. Then we take this value, put it into the f function. So we apply the function, the procedure f to the value of u that we obtained, and so we get the final value. So in general, we have the g function with domain x and range u, and then we use the range u. Please close your microphone. Please close your microphone, whoever joined just now and opened it. Thank you. And then we use u function, and we use the u set as the domain for the g, and finally the range y for the g function. So in principle, the range of x transforms to the domain of u. So we have, let's say, a two-level operation. And so in general, composition of functions, we call it the composition of two functions. We call the g function the interior function or the inner function. It will show up on the screen. And the function f is the exterior function. And before you ask, yes, it is possible to have a composition of more functions. F of g of h of whatever, if you like. And yes, you have to understand the composite functions, because for differentiation, for the next unit, for calculus, it will be important to basically to understand which is the interior function, the inner function, and which is the exterior, the outer function. So it would look somewhat like this. We have this function f, but we need u to produce a value for f. Then we need the function g, which will actually make up that u value. And we put value x into the function g in this case. So as a result, the function g gets a value out of this x. This u equals g of x. As a result, of the action of the function g. Then we take this u value of the function g of x, put it into the f function, and that gives us the function y as the f value of the corresponding value u. And so we say that this is the composite function, and the interior function, oh, I'm sorry, I have not put it in writing. So the g function, this is called the interior function because it is inside. Interior function, or you could say the inner function. And the function f is the exterior function, outer function. And the thing is, not so much putting one function into the other, but rather the other way around, looking at a function and understanding which is the inner and which is the outer function. That is the hardest part, but that is also the more necessary part. And the inverse function and the inverse function, two functions are mutually inverse. So it would be something like this. You put a coin into a machine, it gives you some product, some object, some type of chocolate bar, some type of snack, depending on the value of that coin. So now we can, of course, think of it, let's say, approximately. It's not a very good exact model, but suppose you have a machine which recognizes the coin you put in, or the token you put into that machine, the value of the token. and that each token, each product has a different price. Or in other words, you might have a handful of tokens. Each token is for a different object, for a different product. And depending on what token you put into the machine, it gives you this chocolate or that bag of chips or something. The inverse function would mean we put you say, oh no, I don't like this. It doesn't look very good, this bag of chips. I'll put it back. There's another machine where you put it back and it spits out your own token. So that kind of inverse function, in some countries you get this when you, for example, turn in the empty bottles and get back your money for those bottles. But the inverse function is peculiar in the sense that you should get back exactly the same coins you paid for that bottle. And so to show it in a diagram, we have the range of the function f. As you can see, the range of the function f consists of values, for example, x1, x2, x3. The function f maps these values to onto y1, y2, y3. So for each x value, the function f gives you a y value. And now, if we have another function phi, the function phi that actually takes these y values and maps them exactly back to the same old x values. Then we say these functions are indeed mutually inverse. In other words, the domain of the phi function is exactly the same as the range of the f function, and the range of the phi function is x, that is the same as the domain of the f function. In other words, first of all, inverse if the domain and range exactly switches places. What is domain for one function becomes range for the other, and vice versa. That's an important moment. And then, of course, if you put the result of one function into the other function, that is, if you put the result of f function into the phi function, you should get back to exact same value. So you do f function to get y, then you take this y value, put it into the phi function, and you go back to the exact same x value. Or you may start with the phi function, find the corresponding x value from y, and then put this into f, and you go back to exact same y value. Then we call them mutually inverse. That is, f of a is b and phi of b is a if we have a from the x set and b from the y set. The set x serves as domain for the f function and range for the phi function, and the set y serves as the domain for the phi function and the range for the f function. And as you might see, I have put x in both these cases in the example there where I set these. That is because generally we express all functions as function of y depending on x. Because otherwise, if I write it like this, if I write it x is phi of y, it is basically exactly the same. In case of inverse functions, it would be exactly the same as y is the function of x. Basically, what I mean here is it's the same relation. If I don't change the names of variables, it's the same relation, or it's the same t-shirt simply turned inside out. It's still the same. So in this case, this notation in red does not work very well because it describes the exact same relation between x and y. To get the inverse relation, we also need to change the names of the variables. That's what we will be doing. Now, again, our black boxes or the machines. So we have x value, putting it into the f function, and we get some y value. And now we put this into this inverse function, which is denoted f inverse like this. So we don't generally like phi, we write f inverse if it's a different function, because we have to change the names of the variables. And then we put this y value into the inverse function. What happens is we go back to the old x value. That's the thing. So we apply one function. This is the direct function, the function f, and then the inverse function takes it and goes back exactly to the old function. So we now will write it like this, but please note that in principle and in general, we always use x for the independent variable and y for the dependent variable, no matter which function we are discussing, which simply means that x and y swap places. X and y swap places. To get the inverse function, x and y must swap places. So as I said, we write all functions in terms of x. And of course, a repetition, I'm reminding you, I'm repeating the fact that the domain of one function is the range of the inverse, and the range of the given function is the domain of the inverse. Now, the graphs. If x and y exchange places, simply swap places, x becomes y, y becomes x. Then imagine what happens if the coordinate axes change places. The graph becomes its symmetrical graph with respect to the line y equals x, the bisector of the first and third quadrant. So if we have one function, I will now go and get a highlighter. If we have, let's say, one function, this, marking it in yellow, then its inverse function will have a graph symmetrical to this line, by all means symmetrical. There might be a point where they intersect, but that point will always be on this line, because that's where x and y is equal. That's where x and y is equal. But it's not necessary. Not always these functions actually intersect. These functions, these graphs might not be intersecting at all, and then nothing bad happens. So the function must be 1, 2, 1. We will have this problem with functions that are not 1 to 1. I could sketch a little example here. I will go pen and let's use white. I will sketch a little example. For example, we will have it later on with trigonometric functions. But right now, let's say, suppose we have a standard quadratic function y equals x squared, right? So the inverse function should be y is the square root of x, because if we turn this function inside out, x is the square root of y. X is the square root of y. That is, we swap the names of the functions, of the variables, we get square root. Function is the inverse of the square of the quadratic function. But you see, this is actually something similar to the case in the first diagram, in the first picture. You see, this is the graph of the function y equals square root of x. The graph is not completely symmetrical. Something is missing. Why? Because the square root, as you perhaps remember, means the main root, only the non-negative root. In principle, if I want the inverse relation, I should have both the positive and the negative root to have the perfect symmetry. But in this case, you see, we don't have a function. The inverse is not a function. The given function, the function we started with, the quadratic, is a function. But if we want to write the inverse relation, all of a sudden, it is not a function. Or if it is, then we cannot use one of the branches, one of the parts of this second graph. So we see this is not a one-to-one function. One-to-one means each x value has a different y value. First of all, it is a function, so x value has one and only one y value, but one-to-one means also all x values have differing y values. In other words, we may have to delete one part of the graph, one part of the function, part of the domain, in order to be able to make this inverse function, actually. So one-to-one. In other words, the function values must not be repeated. Not only all different for different, not only only one y value for each x value, but also without repetition. In other words, the function values do not repeat. Y values do not repeat. Which means, for example, the trigonometric functions, sine function, cosine function, create problems for us because the values of those are repeated. Even the value of the quadratic function is repeated at some point. Two x values having the same y value. That's very bad because then we have a problem with the inverse function. So the function by itself is good, happy, and all right. Problems arise only when we are attempting to create the inverse. Now, finding the inverse functions. Okay, how do we do it in practice? And yes, we will need to do this. This is necessary again. To find the inverse of a function, let's say, I am creating an example. So suppose we have something very simple, a linear function, y equals 2x minus 5, and I denoted the independent variable x in blue and the dependent variable y in red, just so that we can see what happens. So what the first thing we do is we exchange the names of the variables, because we don't only want the same relation expressed written differently, because you can transform formulas, and when you transform the formulas, the same formula works. It's the same formula still, it's simply transformed. But to have the inverse function, that is to have an inverse formula altogether, yes, we do need to change the variables. So the first thing is we exchange the names of the variables. So for the inverse function, remember, what was independent variable now will be the dependent variable. And what was the dependent variable will now be the independent variable. In this case, I simply mark the independent variable in blue and the dependent variable in red. And this is necessary because the domain and the range must swap places. That's why we do this. Then we express the new y from the equation. And that is x minus 5 equals to y. Evidently, it's wrong. Actually, a mistake. X plus y. X plus y equals to y. If I move this to the other side, to the opposite side, evidently it has to change the sign. That's an error in the presentation, sorry. Then it's still plus. We divide both sides by 2. And now we have this inverse function. This is the inverse function. I could, in fact, rewrite this as y equals 1/2 x plus 5/2. Writing it in the form of linear function, I simply verify the graph of this is a straight line. The graph of this is also a straight line, of course, because they are symmetrical. They must also have the same shape, different position, but the same shape. So we can even imagine the way it looks. 2x minus 5, that would be a graph looking like this, the first function. Y equals 2x minus 5. Remember, minus 5 on the y-axis, the y-intercept. The slope, rise over run, is 2, approximately this. And then this other function, 5 over 2, 5/2, when x is 0, then y is 5 halves, and 1/2 x, that means the slope is approximately this. And you see how these two graphs are again symmetrical with respect to that bisector. I will sketch in the bisector as well. So the line of symmetry, y equals x. You can see the first line, the white line, 2x minus 5, is symmetrical to the other one. I will make it green. So this will be, oh, sorry, didn't change the color. Okay, do it, please, green. So this will be the green. This is the second, this is the inverse function and the graph of the inverse function. This is what happens with linear functions, with straight lines, and it should happen with everything. But you see, yes, we need to verify domain and range may need. Because in this case, this is one-to-one very clearly. Every x value will have a different y value, so we have no problem with linear functions. Linear functions are 1, 2, 1, because each x value will have a different y value, but we know that not all functions are like that. So in this case, we don't need to verify anything. Let's have some examples for finding inverse functions, because at the moment, this is the most urgent part, finding inverse functions. So what we will do is, we had an example with the linear functions. So let's remember, the first thing we did was change the names of the variables. That's the first thing we do. Actually, it is also possible that we, first of all, express x and then change the names of variables. That's also a possibility. It's not a mistake if we start by expressing x from this function and then change the names of variables. That would not be really a problem, the order in which we do it. So we start from y equals x, 4x plus 5 divided by 3x minus 7. So we change the names of variables. That is, now we write x equals 4y plus 5 divided by 3y minus 7. In other words, what was x in the function now is y, and what was y in the given function now is x. So now we need to express y. Second step, we need to express y from the given function, from the function that we obtained. This is why you needed to be able to express a variable from a function. And that's why we did it in elementary mathematics. So to express a variable, remember from the elementary mathematics, that something that I mentioned several times, we don't like fractions. We would like to write everything in one line, which basically means let's simply multiply both sides by 3y minus 7. And so we have 3yx minus 7x simply by multiplying both sides by 3y minus 7. Pure algebra. Multiply the left-hand side by 3y minus 7, multiply the right-hand side, so the denominator and numerator, these two expressions cancel out. We have 4y plus 5. Now we need to express y. Let's move both y terms to the left and both terms that do not have y in them to the right. So we will have 3yx minus 4y, moving the y terms to the left-hand side, and 5 plus 7x to the right-hand side. It's important that when we express the variable from an equation, it's important that we actually pull it together to one position. It's unacceptable to have it in more than one place. So we pull these together to the left-hand side, leaving nothing with y on the right-hand side. Then we take the common factor y out of parentheses, in front of parentheses, the common factor taken out. We have 3x minus 4 in the parentheses. And the right-hand side remains as it is, and I'll write 7x plus 5, starting with x. And now we divide both sides by 3x minus 4. That is 7x plus 5 divided by 3x plus 4. Okay, there we go. And just a moment, let me see. So we had minus, we had plus, and we had minus. So this had to be minus, of course. Sorry, this had to be a minus. So interestingly enough, you might notice that, for example, 3 and 5, if we compare the two functions, the given function and the inverse function now, 3 and 5 are actually in their old places. And what happens to 7 and 4? They change places and also they change signs. We had plus 4 in the given function. Now we have minus 4 in the inverse. We had minus 7 in the inverse function, but we have now plus 7 in the inverse. So this is something somewhat interesting. And you might have a hypothesis, you might even be able to prove it, but I'm writing down the answer. So the inverse function, and I still remember, we still write it in terms of x, the inverse function is f inverse is 7x plus 5 divided by 3x minus 4. One thing about inverse functions, and I say that people generally make a mistake with that. For example, for inverse trig functions, which is why we will use a specific terminology, this f to power minus 1 means f inverse. It doesn't mean turn it upside down. Inverse is not reciprocal. So with numbers, we are quite happy, and expressions 3 to power minus 1 is 1 divided by 3. But for the inverse function, it's not turn it upside down. It's not turning the function upside down. It means something completely different. Also, when you have any type of expression, if you write, for example, 4x plus 5 over 3x minus 7 to the power minus 1, then you would turn it upside down. It's not inverse. Only the notation f, seemingly power minus 1, means f inverse. Whenever we apply this to expressions and numbers, it means reciprocal, turning it upside down. Only when we apply it to the symbol of function, it means inverse. Like with inverse matrices, the inverse matrix is not the same as 1 divided by the matrix. We cannot divide by matrices. From linear algebra, for example, there was a comparison between power minus 1 and inverse matrix. There was some kind of similarity. And yes, there exists some kind of similarity with functions just as well, but it's definitely not 1 divided by. With algebra, yes. In algebra, we use this symbol to denote reciprocal number, that is turning the expression upside down. In calculus with functions, or in pre-calculus at the moment, with functions, it means inverse, completely inverse. Now let's simply check the range and the domain. We see that the given function, for the given function, the domain is all numbers except 3x minus 7 cannot be equal to 0, right? So x cannot be equal to 7 over 3. And for the inverse function, the domain of the inverse function will be 3x minus 4 cannot be equal to 0, so x cannot be equal to 4 over 3. They are not the same, of course, they are different functions, but we can conclude that perhaps the domain of the given function is the range of this inverse function. That could be verified, in fact. That could be verified. At this moment, we are not doing this. You will have to take it for granted at the moment. This is a one-to-one. Yes, this function is one-to-one. This is one-to-one, so it has inverse function with the full complete domain and range. Why this function is one-to-one, we will see it at a later example. Not at this moment, but this needs to be addressed. This kind of function where we have ax plus b over cx plus d as the quotient of two linear expressions, this kind of function is a function one-to-one, and not today, but next time, I think on Friday, we will spend a few minutes discussing this type of function. Now, next. Another example for finding inverse function, a quadratic function. And you see that I have marked the domain for this given function. The given function has domain from -1 to plus infinity. In other words, we don't have the complete function. Remember, the graph of this function is a parabola, which means the symmetrical graph of the inverse function could be a parabola, but then it's not a function. So because of this problem, I cut half of the parabola, the right-hand half of the parabola, because the vertex of the quadratic function, remember that the vertex of the quadratic function, we discussed that in elementary mathematics. The vertex of the quadratic function would be minus b over 2a, the x value, that is -2, divided by 2 times 1, that's -1. That's exactly where the vertex is. So I am simply cutting off the left-hand side, and I will use only this right-hand side of the domain so that we get 1-to-1, to make it 1-to-1. So this makes it 1-to-1. And now we can deal with the range, with everything. By the way, the range of this function, then we know the parabola ends going up. At -1, we have the minimum point, right? Because of that parabola. So let's see the f value, the function of -1, to find the x coordinate or the vertex of the parabola, which will be the minimum value, of course. We have -1 squared plus 2 times -1 minus 3. 1 minus 2 minus 3 is -4. So the range would be from -4 to plus infinity, because the function is going upwards. So -4 is the minimum point of this function. And by the way, now you see that quadratic functions can be considered, these parabolas can be considered from the viewpoint of functions. And remember, they could be considered from the viewpoint of analytic geometry as second-order curves. Two aspects that investigate perhaps different ideas with this function. And so let's do it. So the first step, exchange. So if we have y equals x squared plus 2x minus 3, then for the inverse function, we have x equals y squared plus 2y minus 3. We completely exchange the two variables. And now the rather difficult task is to express y from this. We have two options. We have two methods of doing it. One method would be, let's pretend it's a quadratic equation and solve it for y. And the second method would be, perhaps we can do it somewhat more easily, that is by completing the square. So x equals, to complete the square, to simplify the whole thing, y squared plus 2y, and to complete the square, the third number should be, to make it a perfect square, it should be plus 1, because then we have the perfect square. And to get minus 3, which is actually there, we need to subtract 4, evidently. No hope otherwise. This has to take place. And that means that x is y plus 1 squared minus 4. To express y, I can now write y plus 1 square actually equals x plus 4, leaving only y expression on one side and moving everything that does not contain y to the other side. And now I say y plus 1 could be, because the square is x plus 4, y plus 1 itself could be positive, or it could be negative square root. Remember that there are two square roots, because the squiggle, the radical sign, means the main root, the non-negative root. But in principle, I know that if, for example, a square is 9, I know that a is positive or negative square root of 9. That is plus minus 3, of course, but it doesn't matter at the moment. Now I have y equals, moving 1 to the right-hand side, minus 1, plus or minus square root of x plus 4. And now I consider the third part, I consider the domain and range. For this function, the domain must be the same as the range of the given function. The domain of the inverse function, this one that I am writing here, has to be from minus 4 to plus infinity. And the range of this function has to be the domain of the old function, that is from minus 1 to plus infinity. Y values are about range. The y values are about range. Now have a look at this. Minus 1 plus minus. Minus 1, to go in the positive direction from minus 1, we need to add that square root, not subtract. If we subtract, we get less than minus 1. We need to add that positive root. And remember, we had something similar with positive negative radicals in analytic geometry when we had half of a curve, when we were discussing the half circle or half the ellipse or half the hyperbola. It was a similar situation, actually the same idea. And so we see that it requires the plus sign, not minus. We had plus minus square root. We need the plus sign to go in the positive direction from minus 1. And so the answer will be, f inverse is the function minus 1 plus square root of x minus 4. Note that also, yes, the domain actually does coincide because this was plus. Because you see how x has to be greater than or equal to minus 4 for the square root to exist. For the square root to exist, x plus 4 has to be greater than 0. Yes, this corresponds. So these two, let's make it in something colorful, just to remind you that these two must be the same and that these two must be the same. And at the same time, we look at the formula, we verify that these things actually work, that the domain and the range works. This is what I meant by the third part. Sometimes we may need to verify the domain and the range. Sometimes it's necessary to make sure that everything fits, that we actually do have a function. The other method of solving this could be solving a quadratic equation, that is, solving the quadratic equation, not exactly this, but y squared plus 2y minus 3 minus x, to move it to the other side, equals 0, because the quadratic equation must have a 0 on the right-hand side. So this is actually the third term, the third coefficient. So we see that a is 1, b coefficient is 2, and c is minus 3 minus x. So writing the discriminant would be 2 square, that's 4, minus 4 times 1 times minus 3 minus x. And then finding the discriminant, in principle, you would get the same situation. You would get exactly the same answer, but pretending that this is a quadratic equation involves, see, a compound third term, because we are solving for y. Y is the unknown for this quadratic equation. So this means the c term is compound, it's combined from 2, and that makes it complicated. See, it's not so easy to do. So basically, separating the square is the easiest and simplest method. All you have to remember is and recognize is, of course, the square of the binomial. Okay, so inverse trigonometric functions. We have perhaps just enough time for that. Next time we will have more exercises with more things, but we have time for inverse trigonometric functions because they also will need to be added to your table of basic elementary functions. So this is actually going into the second lecture. So when I do things online, I prefer to do things, let's say, in a combined manner. When we do things in classroom, I do 4th unit lecture 1 and then 4th unit lecture 2. In this case, I am a little bit combining both lectures today and combining exercises from both lectures next time, more or less. So the inverse trig functions are not in that table. They are in lecture number 2. So this means you need to probably take note of this. So first of all, remember from school, remember the graph of the sine function. It's the red one. It's the red one. So I will probably take the highlighter and simply this is the graph of the sine function. And of course it will go like this. Infinitely, right? Periodic function, a periodic function. A periodic function means after a certain period, after a certain segment on x-axis, the values and the graph repeats completely. Complete repetition. Now, if we want the symmetry, see the blue graph. See the blue graph. The blue one is the graph of, just the symmetrical curve. I'm saying symmetrical curve, I'm not saying the inverse function. We see that it actually does not pass the vertical line test. So like we are putting an exam, to this blue graph, and we see, of course, the vertical line test fails. So this is not exactly the complete inverse function of the sine function. To make it work, we need, let's see, I'm now erasing things. Erase all on this. So to do that, what we actually need is to cut down the domain to make sure that, first of all, 1 to 1. What does 1 to 1 mean? We need 1 to 1. It means that the sine values cannot repeat. This means that, for example, if I take this part of the sine graph, I cannot take all of it because the y values are repeated. I can only take it to the highest point. Because after that, the values go down and repeat the old values. So it's not 1 to 1 after this. So at this point, and it's of course pi half, the right angle, after which the sine values repeat, but it's the point where we cut off the domain of the sine function at the moment. Now, on the left-hand side, again, if we go further left, further than this point, minus pi half, the values of the sine function again get repeated. So this is where we have to cut off the graph of the sine function. And that means the symmetrical graph, of course, of the inverse sine function has to be cut off symmetrically in the y-axis. As a result, we see, first of all, the domain of the arcsine function is the same as the range of the sine function. The range of sine function is, of course, from -1 to 1, because the sine values are within the segment, they cannot go out. Now, the range, we artificially, see, we already cut the range, or cut the domain of the sine function artificially down. So this will be domain of the sine function cut down already to make it 1 to 1. And then, yes, we will have the range of the inverse sine, arcsine. We will use mostly arcsine. I would very strongly advise you to use the notation arcsine. That's for several reasons. Another reason is when you cheat during a test, your online applications don't use arcsine. They start writing everything as sine inverse, like this. I know all online applications use this notation. So when you switch from arcsine to this, I immediately suspect you during a test. That's a warning in advance. And therefore, I do not like this notation, especially because there are some people who think that when you start writing this, it becomes 1 divided by sine x, which is not true. Although, yes, I understand your calculator generally will use the inverse notation if it has it separately. If it's very scientific, it will simply have f inverse. But for arcsine in writing, we do use arcsine. It means sine inverse, but we write arcsine. The arc of the sine function. If you remember, the sine function actually is, well, you should remember, the sine function is, we have the arc corresponding to the angle. The arc length is this x value, if the radius is 1. And then the sine value would be the point on the vertical axis. Arcsine means we have sine value, we are finding the arc. That's why we say arcsine. We have the sine value and we are finding the arc x, arc length x. That's why the name arcsine. And actually the graph of the arcsine is this. So the cutoff parts, this is slightly distorted. This graph is slightly distorted. I should have changed a little bit. I should have stretched it vertically a little bit. But in principle, you see how the graph corresponds to this cut down blue part of the diagram previously. This part is the graph of the arcsine function. We see that the arcsine function is increasing in its domain, so it's increasing, a function increases in its domain. The minimum value is, of course, minus pi half, the maximum value is pi half. So the arcsine function, actually, you see, it's defined on a small segment, its domain is a small segment, and its range is a small segment. So a function that is extremely limited. Similarly, for the arc cosine, we need to cut down the domain of the cosine function. I will do a very quick sketch to show you how we cut down the cosine function. So that was sine function, sorry, that's wrong. Let me erase. Okay. erase all ink faster. The cosine function starts at 1 and then decreases and then increases and then decreases. This is the cosine graph. So in this case, we see we cannot even use these negative values from the cosine domain because starting the positive values, we would have a repetition there. So basically, this is where we cut off. We have to get rid of this part. And then here we see, okay, decrease, 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 decrease. And then it starts, as soon as it starts increasing again, we see that repeated values of the function happen. So the value pi, where the cosine value is -1, has to be where we cut off the cosine graph to be able to make this symmetrical arc cosine graph like this, which means the range is from 0 to pi. The range is from 0 to pi. Range of our cosine function. But in principle, the domain is the same. The domain is the same. The shape is the same. It's only shifted, just like with the sine function. Cosine and sine functions have the same shape of graph. They are just a bit shifted. Now, the next one, arctangent. For arctangent, if you remember the tangent graph, now I need to remind you, the tangent graph, the tangent function, is actually defined not for all x values. You should remember that much from trigonometry, that the cosine graph looks like consisting of separate parts. Cosine graph like this, cosine graph like this. In this period, again, cosine graph like this. So at the points pi half, odd number of pi halves, the tangent value is not defined at all. Because there, remember, tangent is sine divided by cosine. And if cosine is 0, tangent cannot be found. Tangent is not defined. So at these points, in fact, the tangent function is not defined, which means the values repeat in each period. In sine and cosine function, the values did not repeat within a period, but within a half period. With tangent, within a period, so from minus pi half to plus pi half. And so the tangent range is all real numbers. So that's the domain of arctangent. The tangent cut down domain is from minus pi half to pi half, not counting the ends, open-ended. And similarly, the range of the arctangent is from minus pi half to pi half, not counting the ends. And the graph of arctangent function is this, a little bit too large for this, but you get the idea. We see that when x tends to infinity, x goes to infinity, the tangent value gets close and closer to pi half. That's because when the angle goes closer to pi half, then the function value actually goes off and becomes very, very large. And when tangent value goes close to negative pi half, then the angle value, the tangent value goes down, 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 very large negative, which means when x value goes to something very, very negative, far away to the minus infinity, the arctangent value actually simply goes very, very close to this minus pi half, the inverse trigonometric functions. All right. I do believe, the cotangent is very similar to the tangent function, to the arctangent function. This information will be in your lecture file. We see that the domain is still the same, all real numbers, and the range is from 0 to pi, and the arcotangent function is decreasing. You will see why when you compare the graphs in the table of functions. So, but I repeat, the inverse trig functions, these arc functions, are not in that table. In the first file in the first lecture, these appear in the second lecture. As I said, when doing things online, I mix the lectures a little bit. Not much, but a little bit. So I was using the opportunity while we are discussing inverse functions, demonstrating some very, very important inverse functions. All right. Now I'll say goodbye to those who are not doing elementary mathematics till Friday. Those who do elementary mathematics, I will see you in about half an hour. Some people have been asking about retakes. The retake day is set to be next Tuesday, the 20th of April. I will put it up. I will put it up in Ortus. So in the afternoon, starting from, I do believe, 5:30. So you will be able to retake the second and third unit test. I will set up the application form so that I know how many people to expect. However, okay, I do worry a little bit about those people who never attend lectures, but that's not your worry, that's theirs. So those who need to retake, who will need to retake the second and the third unit test, will be able to do it on Tuesday. The next thing that you should know, the midterm examination, that is an exam regarding the first 3 units, takes place next Friday. That is the 23rd of April. It will last somewhere between an hour and hour 30, so most likely 75 minutes. It will cover the first 3 units. So you can imagine it as a combination of the first 3 unit tests, although not exactly, perhaps, but it will be with respect to the units from 1 through 3. However, only those people who have written all 3 unit tests are accepted and admitted to the midterm examination. So again, it probably does not apply to you because those are the people who never come to lectures. There are people who have written none of the 3 unit tests. So they have no hope because I will not allow to rewrite more than 2 unit tests on Tuesday, only the second and the third. For the first unit test, the time has gone at the moment. So all those people who missed with purpose or accidentally or by circumstances, and I do suspect that there were some people who simply decided not to write the unit test, not to write the third unit test then and wait for the retake. I am pretty much inclined not to allow them to do the retake before the midterm because they don't deserve the midterm. The midterm retake will be much harder to be admitted to. So please make sure you attend lectures, you write the unit tests. I made this warning in the first lectures in February. Not many people paid attention to that. So this epidemic, of not coming to the unit test and then applying for the retake has to end. If this happens, if you cannot come to the unit test, you have to provide a documented excuse. If you are so very sick that you really feel very, very ill, I understand that can happen, then I need a doctor's note. If you have, a visa appointment, I need a document demonstrating that you actually do have a visa appointment for that day, and that's it. I will not accept your word anymore because this has become an epidemic. Please note, and I will put this in writing in Ortus. I already have put in writing about these visa applications, which can be understood on one hand, but everybody at the same time sounds very strange. Very, very strange. So I will actually require documentary proof for your non-attendance. All right. If the retake mark will be lower than the first time, generally you should get the second mark. The second mark. If you retake, you are supposed to improve your mark. So if your improvement is negative, that is, you have had time to study extra and you improve it negatively, then you deserve the lower mark. So please count on that. If you want to just improve your mark, if you are sure you can, fine. If you are not so sure, then think again. But of course, the failed tests should be retaken, although it is not a requirement to pass all the unit tests. However, your unit test marks will influence perhaps your final mark. All right, I have been talking a lot. So now it's time for me to have a little rest. I hope everybody has written their name in the Zoom meeting chat, so that I can take the attendance. And those of you who are required to do elementary mathematics, I will see you in, well, now it's like 25 minutes probably.
Thank you, Professor.
You're welcome.
Thank you, Professor.
Yeah, thank you, ma'am.
You're welcome. See you next time.